Any object with charge is surrounded by an invisible electric field. We picture the invisible electric field by imagining what that charged object would do to a positive 1 coulomb. In the case of a negative charge would attract the positive 1 coulomb, so we say the electric field around a negative charge is always towards that charge. Similarly, the electric field around a positive charge, since it would push the positive charge away, the electric field around a positive is always away from the charge. If we have two charges and they're close enough together that their fields overlap, the overlap of the fields creates a force, and the overlap of the field actually stores some energy. Sometimes we call that electric potential energy. If we take a charge and we move it relative to the other charge, that results in a different amount of overlap. The different overlap leads to a different force and a different amount of energy stored in the fields. If we want to know how much work it takes to move a charge from one position to another, we need to look at the change in that stored energy. When we start crunching out examples with numbers, it's important to remember work is a scalar and negative work has a meaning to it. If a charge is being moved into a position it would have naturally moved on its own, if it's being moved in the same direction as the electric force, then the overall work done is negative. If a charge is being moved against the electric force to a position it wouldn't naturally go, then the work done is positive. And again, since energy and work are both scalars, the sign of the work is important, so as we're dealing with positive and negative charges, it's important that we put signs into our equations. Before we do an example, we can kind of write out what our equations would look like. The work done is a change in electric potential energy. Electric potential energy, if we're talking about charges, is kQq divided by r. K being that electric constant, Q for the one charge, that's a Q, Q for the other charge, divided by r, minus K, Q, Q, that's another Q divided by r. To differentiate our r's, I'm going to put a little dash to indicate the final r. Change is always the second minus the first. If you look at those two terms, they have a little bit in common. I'm going to do something different. I'm going to factor out just one of the q's. Then we're left with kq over the second r minus kq over the first r. I'm doing it this way because kq over r is often referred to as electric potential. So what we've just sort of shown is that work is equal to the charge that's being moved multiplied by the change in electric potential difference. Multiplied by the change in electric potential. Sometimes we call that electric potential difference. So work is Q times the change in volts. If we go back to this equation, we really could have factored out more. Oops. If we factor out the K, the big Q, the little q, the work is 1 over the final r, subtract 1 over the original r. Let's try one. This kind of matches that first picture I showed way back on the first page. If we have a negative charge and we move it farther away from another negative charge, negative charges would already have wanted to get farther away, so this should be a case where we get negative work. It would have drifted away naturally, so we don't have to do any work to get it to go farther. Like we talked about before, work is going to be the change in the electric potential energy. Like we showed before, we can factor out the K, Q, Q. Factor out the K, Q, Q. We're left with 1 over the final r minus 1 over the original r. For this one that I made up, if we plug in the numbers, 9 times 10 to the 9 is the value of K. The charge I made up was negative 20. It's important that we put in the negative. It's in millicoulombs, so that's times 10 to the negative 3. The other charge I made up was negative 5, again in millicoulombs, times 10 to the negative 3. And hindsight, those are really, really big charges, so we're going to get a big number at the end of all this. The final R was the 25 centimeters away, so that's going to go in first, 1 over r. The original r was 10 centimeters, so that goes in second. I kind of ran out of room, so there's a multiply at the end, and then we've got to deal with that brackets, the 1 over the 0.25 and the 1 over 0.1. That's supposed to be in brackets. So a little bit messy if you get your calculator and crunch that out. Again, a millicoulomb is kind of big, probably would have been smarter to do microcoulombs. When you crunch it out, you get a negative number. That shouldn't surprise us, but because of those big charges, it actually ends up being a lot of work. Negative 5.4 million joules.